Alright, now we're going to be learning about the other type of progressions. So we learned about the arithmetic sequence, now we're going to learn about the geometric sequence. Alright, again the big question, what is a geometric sequence? Okay, so I have two sequences over here. For the first sequence, I'm just multiplying by 3. Right? And for the second sequence, I'm multiplying by negative half. So this is what you call a common ratio, which we denote as R. Alright, for the first sequence, the common ratio R is just 3. And the common ratio for the second one is negative half. Okay, now let's look at some of the formula that we're going to be using, okay? The first one, okay, remember this is all in the formula booklet, so don't worry about remembering them, but it's good to know, okay? Tn is just T1 times R to the power of n minus 1. Okay, so let's try. T1 is just T1, T2 will just be T1 times R. Okay, because we're taking n as 2, right? T3 will just be T1 R squared. T4 will just be T1 R cubed, and so on and so forth. Alright, and Sn is just T1 times 1 over R to the power of n whole thing over 1 minus R. Okay, let's try a question. For separate AP and GP, the first terms are both 1. Additionally, it's given that the third term of the AP equals the fourth term of the GP. Okay, so let's write down what we know. Okay, for the AP, we know that T1 equals to 1. And T3 we'll know as T1 plus 2D, which is just 1 plus 2D. For the GP, we know that T1 also equals to 1. And T4 will be equals to T1 R cubed. Or just 1 R cubed or R cubed. Alright, and we know that the common ratio of the GP is 3. So this is just 27. Right, I'm just directly applying this formula, by the way, and for this one, I'm applying the AP formula for Tn. Alright, since we know that these two are equivalent, we can say that 1 plus 2D will be equals to 27, which means that D equals to 13 after some algebraic manipulation. Alright, now similarly, if we want to show that a series is a GP, we need to show that Tn over Tn minus 1 is constant. So why is this so? We want T2 over T1 equals to T3 over T2 equals to ... All of this will be equals to the common ratio, right? We want the ratio of this over this over this to all be the same. We want the common ratio to be the same. That's why we are showing that Tn over Tn minus 1 is a constant. And this constant is just equals to R. Alright, so now we're moving on to the sum to infinity. Okay, this formula is in your formula booklet. Okay, so S infinity is just equals to T1 over 1 minus R, where the mod of R is less than 1. How do we interpret the mod of R as less than 1? This is actually just R is between negative 1 and 1. Alright, so why does this condition actually exist? Okay, let's take a look at some examples over here. Okay, we have the first series 1, 3, 9, 27. Can you see that this series actually diverges, meaning that it goes closer and closer to infinity as it gets larger and larger, right? This is also R equals to 3, and that is why it gets so large. So this does not fulfill this, and hence we cannot use the sum to infinity formula. But over here, on the other hand, this actually works. As you can see, all the numbers get smaller and smaller. This is because R is between negative 1 and 1. So actually, we can use the sum to infinity formula. Alright, so let's actually find the sum to infinity. Okay, S infinity is just equals to 1, which is T1, over 1 minus R. And in this case, R is just half. So we have 1 over half, which is 2. That's your sum to infinity. As you can see, the sum of this actually goes closer and closer and closer to 2, right? Alright, thank you guys for watching this video. I hope this helped you a lot in understanding how to do geometric progressions.